The next item is check dam. This is a very commonly constructed item of work in most of the watersheds so far. Actually, when we analyze the necessity of a check dam, we come to several interesting details. Broadly, the check dams can be classified into two major categories. One is for the purpose of impounding storages of small quantities and using that storage for irrigation purposes by taking canals on either side of the check dam. In such a case, it is usually called as an anecut structure. These anecut structures primarily are intended for diverting the base flows of the streams through gravity flow irrigation canals on either side. For constructing such anecut structures, we need base flows or lean season or dry weather flows in the stream, and they should also have certain amount of continuity in the flows during the crop period. These anecut structures would also impound small storages all along the length of the stream and would facilitate irrigation of lands on either side of the stream by gravity flow canals. This is one type. The second type is for recharging the groundwater. In the watersheds, we are primarily interested in recharging the water into the groundwater. And when recharge structures have to be constructed, we usually call them as check dams. And the need for such check dams for recharge to groundwater we will now study. Hitherto, these check dams were constructed in the valleys of the main stream where there are already some base flows, which means the groundwater is appearing as surface water in the stream course. In such cases, there is no need to recharge to water table because the groundwater is already at a higher level and it is finding its way into the valley that is the stream course. So, in such cases where there is already water table at very shallow depth or water table almost at ground level or the bed level of the stream, there is no need for a recharge structure. Again, when one upstream recharge structure of a check dam is resulting in base flows in the stream and it is flowing down to a lower area in the stream, there is no need to construct one more check dam on the downstream side for the purpose of recharge. Already base flows are there in the stream and there is no need for recharge in such a case. However, any structure constructed in the stream bed would have some water spread, and this water spread is limited to the stream course. It doesn't submerge the lands on either side of the stream. It's limited to the flood zone within the stream course. Any recharge device works on the principle of water spread. Spreading techniques are to be adopted for the purpose of increased recharge. In the case of a check dam, the water spread is very small because it is confined to the stream course, and usually it would be 1 hectare or half a hectare. And when such is the small water spread area, the amount of recharge through this water spread area would also have limitations. Now, in this four waters concept, the new technology that is to be implemented, importance or emphasis is not given to recharge structures in the valleys, recharge structures in the main stream course. The entire emphasis is for recharge structures in the upper areas, in the uplands, and any recharge occurring very near the ridge boundary of the watershed would result in increasing the water table levels in the ridge areas and upper areas, and which in turn would lead to increasing the groundwater availability in the lower areas as well. Now, in the case of the check dams hitherto constructed in a very big scale, the results were not very perceptible in the watershed areas. That is because the upland areas continue to have very deep water table levels, and the benefit that is caused by a structure in the main stream is actually increasing the groundwater availability in an area in the valley which is already favored with good groundwater. So therefore, it is necessary to have a revised technology with regard to recharge structures, giving emphasis on increasing the water spread area. Now, there would be a necessity for constructing check dams in the tributaries of the main stream. In such cases, such check dams can have earthen dam in the stream course and surplus arrangement at the ends, like in a percolation tank. In a percolation tank, the entire structure is an earthen dam and the spilling arrangement would be at the ends, and there would be a surplus course formed from the spillway to the deep stream course. In the case of percolation tanks, we aim at a bigger storage, submerging a few hectares of land. But in the case of a check dam, we do not aim for such submersions of large extents. We can limit the submersion area of such check dams to the stream course, and the hydraulic particulars of the structure, even though it has earthen dam at the center, could still be like a cement based check dam at the center. For example, instead of constructing a cement based structure of a check dam at the stream course and giving the bank connections on either side, it is possible to construct an earthen dam in place of the cement based structure, and when this is done, the cost of the structure comes down to 1/3 of the cement based structure. This is done without changing the hydraulic particulars, that is, keeping the same water level and not altering the FTL or the maximum water level. The hydraulic particulars for the cement based structure as well as the earthen dam structure would exactly be the same. So such check dams can be constructed in the third order or second order streams that is the tributaries of the main stream. But then if a check dam is intended to be constructed in the mainstream course, that is, where a maximum flood of a very high intensity could come up, it is not possible to construct an earthen dam at the central portion of the stream, because the flood discharge would be very high, and to negotiate that high discharge, a long surplus weir would be needed on the flanks. And again, the surplus course may pose problems of erosion and things like that. So therefore, such earthen check dams will have to be limited to the small tributaries of the main stream and should not be attempted on the main stream where the flood discharge is going to be quite significant. Now, I said, in the case of anechoic structures, that is the first type of structure which I said, it is necessary to construct a cement based check dam at the center of the stream with suitable bank connections. These are intended primarily for diverting this stream flow and take water through gravity flow canals for irrigation purposes. These should not be constructed for recharge purposes. One reason why it is not required for recharge is, to summarize, there is no need for recharge in valleys where base flows or spring flows are already occurring. The second reason is the cost of the structure is quite high, would be varying from 1 lakh to 3 lakhs rupees, and the corresponding increase in recharge through a water spread of about half a hectare to 1 hectare is not cost effective. So therefore, if it is intended to recharge significantly in a cost effective manner, we should not resort to a cement based check dam in the valleys where there is a good amount of groundwater already. Now let us study the details pertaining to cement based check dam, especially when it is intended to divert the base flows for irrigation purposes. I am again stressing the word. This check dam is to be called as an anechoic structure, and the purpose of that is not for recharge, it is for diverting the flows from the stream through gravity flow canals for irrigation purposes. Now let us see how a structure of a check dam or an anechoic structure can be constructed economically. Let us study. Now this is the bed level of the stream along the flow direction. That means the stream is flowing like this, and this is the bed level. A concrete or masonry body wall of this design can be constructed over a concrete apron. Now the design of this body wall is having certain features that is intended for having the maximum coefficient of discharge. For example, the downstream slope is half to 1, and the angle it makes here is 90 degrees, and the angle it makes to horizontal for this slope is 26 degrees, and this is whatever is the slope that is obtained while providing the base width. That would be the slope here. The base width as well as the dimensions of such a structure are given in ready reckoner tables that are supplied with the guidelines. Now such a body wall profile has got a very high coefficient of discharge, which means that for a smaller length of a body wall, we can discharge a higher discharge when compared to a low coefficient of discharge. Or in other words, with a lesser depth of flow, we can discharge greater